So now we're going to start talking about enzymes. And the reason we're going to spend a little bit of time on them is because enzymes are going to play a huge role in tons of the processes in all these next chapters we're going to talk about. So enzymes are going to be catalysts, which means they're going to help chemical reactions to happen. And what they're going to react with are called substrates. So enzymes come together with a substrate, and that's how a reaction can happen. So they're going to come together, and then that's going to form what's called an enzyme substrate complex. Now, if you look at this picture right here, you can see that the blue is going to be the enzyme, and that kind of purpley pink is going to be the substrate. And what's going to happen is the substrate has to fit in perfectly into that enzyme, and the place where it's going to click into place is called an active site. Now, in this next one, this is a little bit more of a simplified drawing, but I think it shows it a little bit better. So you can see here's the substrate, here's the enzyme. It has to click perfectly into place for that to actually work. So that's extremely important. And then what can happen is either the enzyme is going to form a new molecule or it's going to break two molecules apart. It totally depends on the type of enzyme and what reaction is happening. Now, another thing that enzymes can do is make enzyme complexes. And that would just be a whole bunch of enzymes together. And it kind of works where if, say these were three that were working together, whatever the product was of this reaction would go to this one, and then whatever the product of that reaction was would go to this one. And that makes them a little bit more efficient. So there's a couple of reasons why. One is if these three are all kind of tied together, then they're going to be able to turn and meet the substrates whenever they come into contact with them. The other one is that since they're all close together, when the product of one leaves the first one and goes to the second one, then you're going to eliminate the possibility of side reactions that you don't want to have happen. And then the third one is that you're just more convenient and it's just a little bit more efficient. So you can think of a multi-enzyme complex kind of like the Walmart of the enzyme world. It can do everything in one spot. Now, one thing is that not all biological catalysts are going to be proteins. Or you can also have what are called ribozymes, which are going to be RNA-based ones. Okay, now there's going to be a couple of things that will affect an enzyme's ability to work. One of them is going to be temperature. So as you know, if you increase temperature, you're increasing molecular movement. So that means you could increase the chance that something is going to collide with something else. So if you're trying to get an enzyme to bump into a substrate, if you heat it up, you could increase the chance that could happen. When you do the Benedict's reaction that we talked about with that blue turning to orange and how you had to boil it, that's a perfect example of how temperature could help those work better together. And if you think about it, we have that going on in our bodies. If you look here, this is showing how different enzymes are going to work at different temperatures. So in our bodies, we have an optimal temperature around 37 degrees or 40 degrees. And if we're talking about enzymes working in a little bacteria that lives in the hot springs, then it's going to have a much higher functioning temperature. So it's going to be species specific and things like that. Another thing is going to be pH. If you look at this next slide, you can see that we have different enzymes in our stomachs and throughout our bodies. And one of them is going to work at a very low pH, and the other one is going to work at a higher pH. Now remember how pH has to do with positives and negatives balancing out in a reaction. And so if you change the pH too much, don't forget that enzymes are proteins, and that could cause attractions, like ionic attractions, that could make them unfold. So that's why they have their perfect temperature that they like to work in. And then the last thing that can affect them is going to be what are called inhibitors and activators. And so just like they sound, inhibitors are going to inhibit how well an enzyme can work, and activators are going to help an enzyme do what it wants to do. So let's first talk about inhibitors. The first one you have listed there is a competitive one, followed by a non-competitive one. So in this picture here, you can see the substrate would like to fit right into this enzyme. And you can see here the same thing. What's going to happen, though, is a competitive inhibitor is going to compete with the substrate for that active site and block the substrate from being able to click in there. So I think of this, I like to compare this to like when you go to the grocery store and you want to get a good parking spot, right? So you've had that experience where you go to the grocery store and you see that perfect parking spot and you're like, yeah, I'm going to park close to the store. This is going to be great. And then the next thing you know, some jerk pulls in front of you and totally takes that spot. That is exactly how a competitive inhibitor works. So you can think of it like that. Now, you've got a non-competitive inhibitor over here. And what a non-competitive inhibitor is going to do is it's going to bind to a site that's called the allosteric site, which is not the active site. It's the allosteric site in a different location. But when it clicks in, you can see that it has changed the shape of the active site, so the substrate can no longer get in there. It's called non-competitive because it's not competing for the same spot. It's going to a different spot to alter the enzyme's shape. So the way I think about this with the parking lot example is those jerks that drive those huge trucks or whatever, and they take up like 3 spots. That would be an example of it. Or someone who parks kind of over to the side so much that you can't get into a parking spot. They're acting like a non-competitive inhibitor. So I have some other drawings here that can kind of show you the difference. So you can see in a normal situation, you have your substrate binding to the active site. Here, with competitive inhibitors, it's competing for that active site so that the substrate cannot click in. And then here, you can see a non-competitive inhibitor has gone in and changed the shape of the active site. And I think I have one more picture to kind of show you, how a non-competitive inhibitor can work. So you can see how that non-competitive inhibitor went into this active allosteric site, and now the active site has changed shapes. So this happens all the time. Like, let's say you have a really bad headache and you take some Advil. What the Advil can do is act like an inhibitor and actually keep the enzymes from going to the substrates that are causing you to have that headache. So a lot of medications are based on that. A lot of drugs are based on that. And that's how they work. And we have natural competitive and non-competitive inhibition happening in our bodies as well. Now, you can also have activators. And what an activator would do, I don't really have any good pictures of it, but an activator would go into this allosteric site right here, and it would actually keep the active site in its original form. So instead of letting one of these non-competitive inhibitors in, it's blocking them from doing that, and that way the substrate can click in. So they're just kind of enhancing how well that active site can work. And we have that in our bodies as well. And so one example of that are going to be cofactors. So in the next little part, I'm going to talk about enzyme cofactors and how those can actually work in our bodies to help us stay alive as well.